Let's look at the stochastic gradient descent pseudocode. Again, just as a reminder, what we've got is f with our x coming in and our theta coming in. And this outputs a y hat. Our loss function gets fed in y hat and y. Loss comes out. We go into our optimizer, and our optimizer updates theta. So this is one loop of gradient descent. Let's look at the code that we actually would use. So what we're going to do is, first, we're going to initialize theta randomly. So we get an initial value of our theta. And then, discussed before, I'll discuss again the fact that we're going to run through our training samples more than once. A single set of run through all the training examples is called an epoch. And so we're going to go through multiple epochs. So we're going to have a loop that goes through from 1 to the number of epochs. And what will we do through each epoch? Well, first, let's just look at completely batch gradient descent, where we do the entire batch of input. Okay, so we'll look at our training set. So we will do something like, let's say, we're going to compute the loss on all the x, y in the data set. And this, however the loss is defined, normally this is the average loss for every one of these. And then we're going to calculate the partial derivative of the loss with respect to theta. Let's call this the gradient. So the gradient equals the partial derivative of the loss with respect to the theta. And really this is a huge vector because we've got many different elements of theta. And so we're computing the loss with respect to theta 1, the loss with respect to theta 2, the loss with respect to theta 3, and so on. So this is actually a vector. And then we go ahead and update theta. So we're going to save theta as a vector, because we're really going ahead and updating theta 1, theta 2, theta 3, theta 4, and so on, all in parallel. So theta minus equals the gradient times some lambda, right, which is our learning rate. This is gradient descent. It's not actually stochastic because of the fact that we are taking all of the x's, y's in the data set and computing the loss and the gradient on all of them at once. If we want to introduce the concept of batches, then let's look at how we would do that. So we would actually add in, so first we're going to randomize the order of the data set. So then we're going to go through the for loop. We're going to say for right, so we're going to go from 1 to the data set size divided by the batch size. And then we're going to calculate the loss on all x, y in the ith batch. So what do I mean by that? Well, let's say we've got 10 elements. So we've got x1, x2, x3, okay, along with the associated y's. And so our data set size is 10, and let's say we've got a batch size of 2. Okay. So the first thing we do is randomize the order of the batch, the data set. So the randomization may take us to, let's say, x5, x3, x8, x10, x1, all the way to the last one is, let's say, x9, and the associated y's as well. And now we're going to go ahead, and how many batches are we going to have? Well, we're going to have, in this case, 10 divided by 2, since I said that 2 is our batch size. So our first batch is going to be this one. And then our second batch, and our third batch, all the way to the fifth batch. Note that there's a sort of an assumption here, the way this is written, that the batch size divides evenly into the data set size. Really what we'll have is the very last batch may be smaller than batch size. And so this is how we deal with the training. We may want to be printing out or saving somewhere the training loss as we go. And of course, the data set we're talking about here is the training data set. We may also want to, let's say, every epoch, we may want to go ahead and calculate the loss for the validation data set. And this will give us an idea of the loss of the validation data set as opposed to loss of the training data set, and let us know whether we start overfitting. In the degenerate case, where our batch size is 1, this turns into true stochastic gradient descent. We randomize the order of the data set, and then we pick one training instance, and then calculate the loss, update theta. The next one, update the loss, calculate the loss, update the theta, and so on, continuing through. It's worth noting here which of these are actually hyperparameters. So if we look at our hyperparameters, what do we have? Well, number of epochs is certainly a hyperparameter. Batch size is a hyperparameter. And we've also got our learning rate as a hyperparameter. The batch size, part of what we are thinking about here is not only how well does the training work, but also how quickly can we train. And as we'll see once we get into neural networks, we're taking advantage of GPUs. And there, this calculation of loss and calculating the gradient, we can do that in parallel for a number of different training instances. We can choose our batch size such that this cost, as we increase our batch size, this cost doesn't increase at all. So to a point such that we can actually fit things in GPU memory, we can increase the batch size until things will no longer fit in GPU memory. But while they're fitting in GPU memory, actually we can just increase our performance because this inner part of the loop is going to run at a constant time even as we're increasing the batch size. So basically what happens is whether we're working for 1 training instances all the way up to k training instances, so this is, let's say, the batch size, and this is the speed of the inner loop. From basically 1 to some k, it's going to be constant. And then, once it no longer fits in the GPU memory, our cost is going to go up.